My name is Egor. I'm an engineer on Cash App.
I'm Benoit Quenaudon, doing Android stuff.
And today we're going to speak to you about multiple things. First of all, it's protocol buffers, gRPC, and Wire. So what is Wire? Wire is a protocol buffers library that we built at Square quite a while ago, actually, and initially was designed as the Java toolchain, basically a compiler and a runtime. And it was specifically designed to generate Android-friendly code. But since the inception of Wire, a lot has changed in the world. So last year, we embarked on a pretty long journey to modernize Wire, and first of all, to teach it to understand Kotlin and to generate Kotlin. And along the way, we actually updated the tooling by adding a new shiny Gradle plugin to the Wire toolchain. And we added an exciting new feature, which is the gRPC support.
And so why would we want to use gRPC? There are a few reasons. And first, you define new API calls via protos. So there is it's really easy to communicate between people. You can check in your repo how your API are designed. It's cross-platform. It doesn't care about which language each party's over the API call will be. We use protocol buffers for serialization, so it's really effective, and it's over HTTP2. This means we can do duplex calls and use streams, which are pretty dope. And so this might seem familiar for some. This is a retrofit interface. So before you were like, okay, I need to ask some server person, what is this URL? Do I need a header? I don't know, whatever. This is done, retrofit is dead. Let's go gRPC. And yep.
Great. So before we start going deep into gRPC and stuff like that, let's talk about protocol buffers in depth. Because protocol buffers is the building block that the entire kind of system sits on top. So protocol buffers is a serialization format that was developed at Google. And some of the features of protocol buffers are that it's a schema-based format. So unlike, for example, JSON, when you don't really have like a specialized schema, it's basically ingrained in the data. Here you have like a separate schema and a separate byte representation, the serialized format. Because of that thing, so because you separate the schema out of the actual data, so the serialized data in protocol buffers is really lightweight. So it's really efficient to transfer and store and so on. So protocol buffers were designed with really strong backwards compatibility guarantees. So it's ingrained in the design, and I'll show you how that works. And there's very rich tooling support provided by Google to go along with this serialization format. So let's talk about schema. So basically, here's an example of an entity defined using protocol buffers. So here, let's say we have some kind of person entity with the fields and so on. Let's actually go line by line and try to understand what we see here. So first line defines the syntax, which is basically the version of Protobuf schema that is used here. So there are just two versions right now. It's Proto 2 and Proto 3. At Cache, we use Proto 2. So this is the format that we'll be focusing on as we talk. So the next line is the package definition. So you know about packages, they're present in Java and Kotlin, and it's basically a mechanism to namespace the protos. And you can't really see it in this example, but protocol buffers supports imports as well, so it allows protos to reference themselves. It's just not present in this example. So the next line, it kind of might seem repetitive because it also defines some kind of package, but you must remember the protocol buffers are platform agnostic. So by default, the schema doesn't know whether it will run on Java or on C++ or whatever. So there's a mechanism called options, which allow you to define, kind of like extend the schema to define platform-specific information. So in this case, it's just like a Java package. So next we can see that there are two types of entities that we can define with protocol buffers, messages and enums. So messages are really similar to like Kotlin types or Java types. And of course the enums, which we all know. Now there's a set of fields in the person message, and you can see that each field has like an int value attached to it. So those integer values are called tags, and they're really important for serialization, also backwards compatibility, and we'll touch upon them in quite a bit of detail going forward. So some of the fields in Proto can have additional rules attached to them. So some of the fields can be required, which means that the serialized data has to have the value for that field. Some fields might be optional, which means you can omit the field. And some of the fields may also be repeated, which means that the value for that field can occur multiple times. So if you deal with that information in code, then that would basically be mapped to a collection of some kind. And Protobuf supports multiple types of fields. So you can see there are multiple flavors of integer values, Boolean, strings, bytes, and so on. Now that we know how the schema looks and how it works, let's look at the bytes at the actually serialized format. So for that, we will take the schema that we've already seen. We'll use wire to create an instance of the person type. Then we will serialize it to bytes and just print them out as hex. So here you see like the hex string of that data. Let's just zoom in and let's actually count how many bytes we have here. And we can see that we only used 10 bytes to serialize this message. So how exactly we achieved this effect? So let's just look into those bytes and see how the data is serialized. So the first byte here represents the first field, which is the tag and the encoding. So you can see that the tag, the value 1 is used for the first field, because tag uniquely represents that field. And also the encoding here is called var_int, which also has like an integer value. Then we just do some bit magic to arrive at the value for the byte. And the next byte in the sequence will actually represent the value for that field. Let's go forward, and the next byte here will have the value which will represent the second field. Again, the tag value here is 2. The encoding here is a bit different. It's called length delimited, which is usually used with strings. Again, we do some bit magic to calculate the value. And with length delimited, the next byte will represent like actually the length of the string that we're trying to encode. And not surprisingly, the next 4 bytes will contain the ASCII values for the characters, like each character in the string. And we'll go forward. We'll take our last field, which has the tag 3. So we take that value. We take the encoding, which you can see is also var_int. Because for enums, the value of the field is basically just the tag of that value in the enum definition. Again, just some magic here. And we get the value as the next byte. So we just use 10 bytes to serialize that message completely, which is pretty awesome. So talking about backwards compat, as I said, protocol buffers use this limitation pretty, like it was part of the design. So this is used when you evolve your schema. So naturally, if you have like a system, then the schema will change over time. So you want to be able to basically you want your clients having different versions of the schema to still be able to deserialize the data. And let's see how that works with Protobuf. So for that, we will just use our old schema, and we'll just label it as version 1. So it's like some snapshot of our schema at a certain point in time. We'll just create a message, we'll serialize it, and we'll hold on to that value. And then we will try to evolve our schema and deserialize the message. So first, we change our schema by adding a new required field. And let's see if that works. So we'll try to deserialize it using the new schema, and it will fail. Why does it fail? Because we added a field which is required, and our serialized data didn't have the value for that field. So the parser cannot find it, and unsurprisingly, it fails. Which is an important lesson to learn, that required fields, you have to use them with caution, because they're really hard to either remove from your schema or add to your schema, because you will have like older versions of clients on the network still using the old data. So it'll be kind of hard to maintain. So on the contrary, if you add an optional field, then the serialization works just fine. Because this value was not mandatory to have in the serialized data, so the parser would just ignore it. Let's see what happens if we try to remove fields from the new schema. So if you remove the required field, basically that piece of data just gets ignored. So when the parser tries to deserialize the message, it just finds like a tag that it doesn't understand because it's not present in the latest version of the schema, so we'll just pass it. But still, it kind of like has the bytes for that data, so it's not completely lost. And we see the similar behavior if we try to remove an optional field. Also, the parser can parse it just fine. So what if we try to change the tag value on a field? I mentioned that the tags have to be unique, and it's kind of like a unique representation of each field in Protobuf. So if we try to change the value of the field, the deserialization mechanism will not be able to find data for that field, because it kind of like it lost the key for that value, so it's kind of lost. So it's not the best thing to do to your schema. So naturally, like the fields and tags have to be they have to be defined once, and then you shouldn't really change them. Because a more dangerous situation is reusing the tag, which was already used for a different field. Let's see what happens here. So we get a deserialization error because the data contained the value for a field of type string, and now the tag changed, and basically like now the schema points to an enum, but the data has a string. So the deserialization mechanism just doesn't understand how to parse it properly, and this is a problem. So how we approach this problem is just every time we remove the field, we just document that tag cannot be reused. Another dangerous situation is when you change the type of the field, because in this case, actually, you can see that deserialization doesn't fail, but it gives you an obviously incorrect result. So this can be even more dangerous in practice than just failing serialization. And lastly, if you just rename the field, it's a completely safe operation, because maybe you noticed that the serialized version of the data doesn't mention the field names at all, so they're just present there for the code, so you can rename them as much as you want. It's a safe operation. And the last point to make is that Google actually offers a large number of tools to accompany protocol buffers, which is just compilers and like runtime libraries. And this is the list of languages that Google supports for Protobuf.
So why did we build Wire? So Google is actually supporting Java since forever. And so I could say, why did we build Wire? And I could also say, why not using the Google generation? So we go back to the same protos that Egor defined, 3 fields, small enum of 3 values. And we run the Google Protoc generation tool. And so from this person.proto, we get some person outer class something. So it does stuff. And so we look at the code. There is some interfaces. Now we get a static class of person, which implements things. And so if we go down a bit, we can see it's doing stuff. I don't really understand what it's doing, so we'll skip that. There's a few things. It's talking about descriptors. And we have house occupation, getter. I understand that. Then we go down. It's doing a few things. And so when I copy-paste the code was so long, Keynote said, OK, you stop your full size. And in the ID, you can actually see that it's more than 900 lines for 3 fields, 3 enum values. That was crazy. So the code is not readable for either of us. I counted manually. It was I'm not sure, so it's more or less 95 methods for, again, 3 fields, 3 values. I think that's crazy. So that's why we don't use any of the Google tools for that. And we decided at Square before I joined, so anyway, to create Wire. And so the first release was back in 2013. And we wanted a few sets of values to protect. So first, to be Android friendly, we wanted a small number of methods. We wanted the code to be readable, the closest as it would be if you were writing the code yourself, or better. We wanted to embrace immutability and not play around with anything. Support for chain-border pattern, especially in Java. And all the documentation that would be in the proto file would have to be in the generated code. And so that's a lot of things happen. And now we have wire 3. Yep, wire 3, which includes 3 main features. The first being now we support gRPC services. So basically in proto files, you can define message or service. And up so far, we only supported messages, and now we support service. We generated code not only in Java anymore, but also in Kotlin. And we have now a nice Gradle plugin. So let's look at the gRPC support and what's happening. So gRPC is a protocol for making API calls on HTTP2. API calls mean there is 2 sides to each coin. You can be either the client, like calling, making the call, or you could be the one receiving the call. And so because it also uses HTTP2, we have to take streams into account. And so there is 4 ways you can define an API. So the gRPC keywords is the same for all. You define the API method name, the parameter, the request, and the response. So here we get 1 point, we receive 1 feature. Then here we send a run rectangle, and we get back a stream of features. So the request has to finish first, then we get the response, and wait until the response is finished. Here the client sends a streams as a request, and so the client has to send everything and say, OK, I'm done, and then it will get back a root summary. And so the last crazy thing is duplex, so both can talk anytime, so data is just crossing back and forth. And when both are done, the connection is finished. So that's the 4 different gRPC mode you can have. And so, as I said, there is a duality between who's calling, who's getting called. And so to handle that in the configuration, we added a few configuration. So one, are you the client? Are you the server? Are you invoking the API or getting called? This will affect the generated code. Do you want your method to be suspending or blocking? It only concerns the one-to-one, so 1 request, 1 response. When you do the call, basically, do you want this method to block or not? And so we have only 2 options. And then for server containers, it's pretty standard to do 1 method per interface. And so while in Android, we would have 1 interface with all the API methods, like what we do with retrofit right now, it would be for the server 1 method per interface, and it will help to just separate the code, because for the server, you need to keep states of what is going on. What configuration would you want for a client? As of a default, you could go suspending, which would use Kotlin coroutine, your client, and you don't really care about having 1 single method per interface. For the server, you might want to be blocking server, and let's go 1 single method per interface. And so the generated code would look like this. For the client side, with this configuration, meaning we generate code in Kotlin, we are client suspending, and many methods per interface is fine. And so with the proto up, we'll see what's happening for each part. First, we take the service name, create an interface, and suffix client. It extends a service interface provided by Wire, which is just used in Wire to do things. So one-to-one, it's a basic suspend method, which by definition is not blocking. We get the point, then we receive a feature. When the client sends one object to get a stream back, it gets as a response a receive channel that it would just have to listen to. And because we give back the receive channel, the client, the method doesn't have to be suspending because it's non-blocking by default. The method is just starting the connection and let the request and response do their thing. When the client wants to do streaming, we give to the client a pair of send channel, which would be, OK, client, use that to send your data. And here is the deferred object where the response will be. And when we do streaming, it's a pair of channels, one to send data, one to receive from. And that's it. Wire will add some annotations on each method for housekeeping. And so on the client, the same as in retrofit, we provide runtime implementation. So you would create a gRPC client object, pass it OKHTTP client, give it the URL, build it. And then the same for retrofit, you create, pass it the interface, and you'll get an object from which you'll be able to call the different RPCs set in your service. This is the dependency coordinate that would provide you with a gRPC object, a gRPC client object. And so on the server side, let's see how it differs. We are blocking server, and we want one method per service. So in the root guide blocking server, now we suffix with server, but also with the blocking keyword. That would happen either client and server. One-to-one, no surprise. We are blocking, so no suspend. When we receive one object and give back a stream, we are basically passed all the objects required. We get the request and the sink to write the response to. And because we don't want to depend on Kotlin coroutine here, we provide our own interface, which is as simple as that, just write and close. We have the same when we need to receive a stream. We are passed the message source, which is like a receive channel. Two methods, read, close. We read all the data and then send back the object. And for duplex, we actually get past the same two channels, which are the message source and sink, to get a response, the request, and to write the response back. And the generated code is a bit wrong because we were single method per service true, so it should have been one method per interface. And in this case, the method name would be suffixed in the interface name. Here, because there is no need for gRPC client, no need for coroutine, whatever, you only have to depend on the wire runtime. And so we don't support server coroutine yet. We are going to do it. And we don't support other things yet. So there is no Java generation for service. There is no observable API, nothing like that. At the moment, only coroutine and the message source and sink that I showed.
All right, so that was the gRPC part. I'll briefly touch on how we generate Kotlin code, or specifically the design decisions that went into how we model our Kotlin representation of the protocol buffers. So here's an example of a generated code, of a generated class, more specifically the header, because like most of the stuff just happens in the primary constructor. I just grayed out the data, the stuff that you shouldn't really care about, but the interesting part is that we define the primary constructor, we declare all of the properties inline, and we have default values for the parameters. So it kind of looks similar to data classes, right? They're actually very similar to data classes, but not quite. And the problem is that we stumble upon a limitation of not being able to declare just a primary constructor parameter in data classes. So you have to declare a property inside the primary constructor. In this case, it was the unknown fields, which is which is basically a property inside the message type, which is the super type for all the protos. And we didn't want to change our code too much. Also keep the interoperability with our Java generated code. So we just decided to generate all of the usual boilerplate ourselves. Because in our case, we're a compiler, right? So we just like take the schema, generate Kotlin. So we can do it instead of the Kotlin compiler. So you have the equals method generated, you have the hash code, you have the toString. So they're still present, and as a consumer of this class, you don't really care whether the implementations come from a data class or basically wire. Another thing is that we deprecated the builders. So builder was a type that would be generated for each message, and it will allow you to kind of like construct the instances and basically reuse them. So we decided to deprecate builder because Kotlin classes are very powerful in terms of how you construct them and create immutable instances. So we provide default arguments. So you can only pick the number of arguments that you want to pass to create an instance. And also we generate the copy method, similar to what Kotlin compiler does for you if you use the data class. So if you want to create copies of that instance, it's also pretty straightforward. Next, we could use Kotlin's type system to properly model the field rules. So in this case, for example, ID was the required field. So for that one, we could use the non-nullable int type, and name was an optional field. So for it, we will use the nullable string type. Next, by default, the Kotlin code that we generate is not platform specific. So it doesn't really interoperate with Java properly. But we have a compiler flag that you can pass in if you care about the good interoperability with Java. And if you pass in that flag, it will just generate additional code for you to make the interop story better. So we'll just add JVM field to the properties. It will generate all of stuff related to builders. So you can see that it's actually the builder implementation that you can use. And a huge and very exciting thing about the wire runtime and basically the generated code, that by design it's supposed to work on all platforms that Kotlin Multiplatform supports. There's a small asterisk there, is that it's still an upcoming feature. We've been testing mostly with Kotlin 1.3.40, and it was breaking our code because of some of the bugs still in Kotlin Multiplatform. So we basically have all the setup for multi-platform, but specifically like that issue that we've seen was kind of like not allowing us to proceed. But luckily, this one has been fixed in Kotlin 1.3.50. We've upgraded, I think, just a couple days ago, and preliminary tests look pretty positive. So hopefully, we will move forward with this feature. So next. Awesome thing, already mentioned the Gradle plugin. Gradle plugin was contributed by our colleague John, who's here. Huge kudos to John for Gradle plugin. John. Kudos. Gradle plugin is quite straightforward. So what we used to do with Wire before 3.0 is basically the API to the Wire compiler were either command line, so you could just invoke it from the command line, or also the initial versions of Wire came with the Maven plugin. But now in Gradle, what we were doing is just basically registering a custom Java exec task to benefit from the command line APIs. And it's not like a lot of code, but it's still too much code to use something like a library. So the Gradle plugin is quite straightforward to use. It just gives you the Wire extension, which has a lot of configuration methods that you use, for example, to declare the sources. This is basically where your protos live. It could be either like a local directory, it could be a jar artifact somewhere in Maven Central, so it's all supported. And then you declare a number of targets. So think of target as like a language that you want the code to be generated in. So in this case, I'm declaring the target of Kotlin, so I want my protos to be generated in Kotlin. I give it basically the output, the directory where I want my protos to end up. And also there's some filtering options like includes and excludes. Here's a complete list of properties for the Java target. Some things to note is like the Android flag, which will add parcelable implementations to your messages. So you'd be able to serialize them on Android and pass them, like put them in a bundle or stuff like that. And here's the list of options for the Kotlin target. And here you can see the Java interop flag that I mentioned before. So if you pass that as true, then you will get like better interoperability with Java.
So show me the code.
Yeah, let's see some code.
Yo, so we made a sample app. So we show the code quickly and then do the demo. So there is basically 3 modules: app, Protos, server. Protos is where the common messages are generated. Then server will take care of its own RPC generation, and app will do the same. Our proto file looks like this. There is a point message which takes X, Y, some color. Then we have command and update, which basically are request and response. So the command would be from the client saying, OK, I added a point, or I want to clear the whiteboard, which we'll see soon. The update is the server saying to the client, OK, now you need to set up your whiteboard, or here is the list of points I want you to display. And our RPC is called whiteboard. It takes a stream of commands and returns a stream of updates. So basically, the client just sends data whatever they want. The server sends response back whenever they want. And so the proto config uses the plugin as we saw. Wire, we prune the RPC out because we don't want to generate this here. Kotlin target will generate Kotlin code, and for the purpose here, we want the generated code to go in source main Java and not in the build folder. And so the code would look like generated Kotlin code, nothing fancy. Then let's go to the app would be, we define where the protos are, which are backed in the protos module. Here, we don't care about the messages. We just want the whiteboard RPC, so we include it. We want some suspend client, and we don't care about this. The server would be, yeah. OK, yeah. The server, same wire, generate the code in Kotlin. We only care about the RPC, but this time we are not client, we are server, and we want some blocking code. And so this is the generated RPC from the server side, so blocking server. This is the annotation provided by wire, which isn't really important. And then we have our request. We get past both a message source and message sinks. To run the server, we use MISC, which is something developed at Cash App that is kind of open source, but not really released yet. And so our implementation goes here. This is a singleton instance, and every time a client calls the whiteboard method, this gets called. We create a client object, add it to the list, and just process it. And in the process method, nothing fancy. We get we use the update sync to send data to the client saying, OK, set up yourself, and here is the current state of the points. And then every time we receive commands from a client, we need to broadcast that to everyone. So if it's a add point command, we just add it to the list of points. If it's a clear, we clear it. And then for all clients, just write and set the data, and you're good to go. And so for the client, it would be this is our generated interface. This time, instead of getting past the channels, you need to return it. And so we have some code because gRPC requires HTTP2. For the demo, we needed to embed the certificate, so there is a lot of boilerplate, but the important piece is here. we create a gRPC client builder, pass the OKHTTP client, pass it the URL. And in the main activity, this is where the magic happens. We get our implementations furnished by wire, called the whiteboard, and then we just stored both the send channel and the receive channel. Then we listen to what the server says us to do. If we need to set up the board, we do it. If it's a point, we draw them. And then in the view, we would have a few click listeners. If there is a point, send them to the server. If the clear button is pressed, send it to the server. That's it. That's it. And so we'll see how it goes. So we run the server. You can see that protos are generated. Let's go back. Protos generate the 3 message point, whiteboard command, update. The server generates its own interface, and the client wasn't involved here. And so we'll see how it renders for the client.
Let's do it.
Yeah?
Yeah.
I draw the line.
So we have 2 devices just connected to that server. We'll play some tic-tac-toe, because that's what our app does. I'll just start here.
Oh, I'm sorry. Yeah, my bad.
Okay.
Oh, you support config change, man. Nice. And so
it's a real app.
And wait. Yeah. And so what's really dope about this? Come on, you suck, man. Come on.
I'm not good at this game.
What's really dope is that the client says call whiteboard once, so there is only one API call.
I crashed.
No. And you might have changed color. Can you try to do something? Okay, you crashed now. Thank you.
Okay.
So what was interesting so far was that the client called the API once, and then everything was just duplex calls. The client would send data, it would get data from the server, and that was amazing. I think it's good. Yeah. And so what's next? What's next? No.
Yeah, so we're still a lot of things to work on. Firstly, I guess we really want to finish the multi-platform story and kind of be able to run all of this on not only on JVM, but maybe on our iOS client and so on.
We want to finish some gRPC APIs. Like, I think we should generate some Java interface, at least for the server, because server are slow to migrate, maybe. I don't know. And there are a few things we want to polish around the dependencies. And so, as I said, maybe for Java.
Yeah, and our Gradle plugin is almost ready. Still polishing some things specifically for Android, and soon it's going to be ready to go. All right.
The sample app will end up in the Wire repository. Right now, it's just an open PR that I don't know why nobody is reviewing. Anyway.
Yeah.
And so, yep. And so this is not a two-man work. It's teamwork. So let's give it up for the team. And yep. Thank you very much.
Thank you.